Hello Nastran Ninjas. Today I'm going to go over a demonstration on the usage and functionality of the analysis tool that I've had released for a few months now. I've gotten some pretty good feedback on this tool and I think it's really useful. I hope a lot of you have already had a chance to play around with it, and if not, after watching this demonstration you should be able to open it up and use it, and hopefully you find it useful. So to access the tool, you simply go to the source code page on nastranninja.com. The tool itself is all the way at the bottom. Here it is, analysis tool. At today's date it's version 2.0, it's still beta version. And it's actually been recently updated to include the ability to combine load cases and factor results. So that's a very useful functionality, to be able to combine your load cases in the cases of having thermal results and mechanical results run separately. And also, if you are only running limit cases or maybe even fatigue cases and you need to apply factors to those linear results, you can easily apply those factors with this tool. So in the last video I showed you how to download this tool and open it up. So I've already got it downloaded. I'll just open it up real quick to show you what the user interface looks like. Here it is, analysis tool. There's about 5 inputs, 2 of them are optional at the top. And there's this big text box that allows you to insert a user-defined function. And all the way at the bottom is a big analyze button for when you're ready to generate the results. Alright, so that's a quick overview. Let me just show you what we're going to go over today real quick. During this demonstration we're going to cover how to create an FO6 database. The database is actually how the tool communicates, or rather imports results from the FO6 files. It's actually the main functionality found in the Strangle library currently. And then after that we're going to go over specifying how to specify input files. I'll show you what a combination and a factor file looks like. And then after we have sufficient input in the tool, we'll just run it real quick with a blank form. When we run it with a blank form, it simply grabs the results from the FO6 file and summarizes them in a comma delimited output file. So after seeing that, we'll show you how to include a customized function in the text box, and then I'll show you the output again and the possibilities of using that output for analysis purposes. So back to the tool. First step is to create an FO6 database. Before doing that, I'll show you the files we'll be working with today. There's 2 FO6 files labeled with the subcase number. Here's the combination file and the factor file. Naming doesn't matter, but it does need to be a comma separated in comma delimited format. Here's an example PDF. We won't be covering the details of that. And there is already an existing output in there, but we will be creating new output, so I'll just delete it. And then later we'll see what's inside this demonstration file. It actually includes just a simple function. We'll be running on all the output that we work with. Okay, so let's go ahead and create that FO6 database. To do that, simply click the database menu, and there's only one option, make database, make DB. It brings up this database creator tool. This tool is very small and simple. All you have to do is specify a top level directory and give it a file name to where the database will actually be written to. So let's go ahead and quickly do that. Our FO6 files reside in this directory, so I'll just copy and paste it, and then specify a new file in that same directory. I'll just name it after the BDF we'll be using. I like to use FDB as the extension of these files, but it can really be anything. There's no requirement there. It just stands for FO6 database. Tool kind of disappeared on us. There it is. So these two fields are filled in now. All we have to do from here is hit fill list box. You see it found those two FO6 files that resided in this directory here. But one of the nice things about this fill list box functionality is if there were FO6 files in any subdirectories of this master directory, say, then it would also find those FO6 files inside the subdirectories. So what it does is it starts at this top level directory and then walks through all sub-level directories to find all the FO6 files that may reside. So that's pretty nice when you have all of your FO6 files organized in different folders. They may represent ultimate cases, limit cases, or what have you in each of those different folders, but with one top level directory you can find them all. So today we only are working with these two files, of course. So we've already found them, and I'll just click select all and make database. See some information pop out here. Tells you it's done. You see that it did indeed read those two files. Tells you how long it took. Says two files were written to the database, and then overall how long everything took. So we're actually done with this tool now. We've made our database. Before we move on, let me just cover how the database works. What's going to happen with this database is, obviously it reads in multiple FO6 files, and then all we have to do with the tools we use from the website is to specify that database every time we want to read results from all these FO6 files. And the way the database works is it doesn't actually load all the results from the FO6 files. You notice how quick it was. All it really did was scan the FO6 files and save the locations and the types of the results that it found in those FO6 files. So there's no data, there's no results data being saved inside the database files. Only information. And that approach was taken to save time, since it reduces the amount of time to take to build these databases, and also to save space, save disk space, since you don't want to have two sets of the same results on one computer taking up unnecessary space. The tricky part to all that is this database also needs to realize when things have changed. So there's actually a check for updates function inside the database. Every time you open an old database, it will actually check for updates, and it will tell you if there's a file missing. It actually generates an error currently, And if it finds that there's a new file of the same name, then it will actually scan that new file so that all the new information is saved. So I found that this database approach has worked very well for me. It saved a lot of time and saved a lot of disk space, and I hope it works well for you too, but please let me know if you're having any issues with it. Things can usually always be fixed since the code is open source and I wrote it, so just let me know. Okay, all done with that. So now we have a database. All we have to do is tell the tool, the analysis tool, where it's at. And I saved it over here. There it is. So now the tool itself is ready to read the results, but it also needs a model, because we will be using model information to run calculations later on. So I'll tell it where the DAT file is. It can be a DAT or a BDF file. I just call it DAT file because if there are include statements in there, it's okay. There it is, our example BDF. And so the next step is to specify a range of element IDs of which we would like to gather the results from. One of the limitations for the tool right now is it can only work on one element type at a time. So if you want to analyze a bunch of beam elements, it'll work on a bunch of beam elements, but you can't analyze beams and bars at the same time. You'll have to separate them into two separate runs. It's the same for quads and tri elements, even though they're both shell. It'd be nice to be able to run them at the same time, and that functionality will be included later on. But for now, it's just quads or tris one at a time, or beams or bars one at a time. This seems like a good opportunity to bring up the quick help guide. So I go to help quick guide. I wrote just some helpful information in here. This shows you what element types the tool can currently process. So it can also process seed bushes. So I have a set of quads here already pre-chosen. The nice thing about specifying element IDs is the tool can handle the syntax from Nastran. So basically, if you had Nastran open, you could just select your elements and copy and paste that string into the tool. It can handle colons, it can handle spaces, it can also handle commas if you have a different syntax. But you should be able to copy and paste just the Nastran strings in here. And for this first run, I'm going to turn factor file and combination file off. And now that we've specified these three input options, we're ready to just click Analyze. First thing it does is it opens up the DAT file, reads it, and then it opens up the database and asks the database for whatever element type we've specified. And these IDs. And you can read through this output here. Here's some Nastran output at the top saying how it's read through all the bulk data. And right here, it's saying it's reading the database, the quad forces from those two files, and then it tells you how long it took, and in the end, how many inputs is actually processed for each element. So we've actually created some output. And as of now, you don't actually specify where the output is created. It actually just goes to where the FO6 database resides and creates it there. So here it is. It's named output.csv. We open it up, we'll see everything we get. Here's our load case IDs, our element IDs. Give the same set of element for each load case. These IDs are repeated a few times. That's okay. We get to see what our property IDs are and our material IDs. And we have our force components for each of the quad elements that I've specified. Here's the end plane forces, the moments, and the shears. And over here, far to the right, we have the thickness of each element. So all that is very useful information for a stress analyst. And from here, we could actually just start using Excel to do our analysis on every element. With the thickness, we could calculate all our different stresses given the forces. And we could insert the allowable somewhere here in this spreadsheet and calculate margins of safety. So that's probably the simplest way to use the tool, is just to read all the data from the FO6 files and then run your analysis from Excel. But if you wanted to do something that includes even more functionality, we could include a user-defined function. And I actually have one already written. To access it, I'll just go to File, Open. Find where I'm doing my demo. And here it is, demo.py. And there it is. That's the contents of the user-defined function that I've written for this demonstration. This is Python syntax, of course. I can save it. I can save it as a different name. I could close, or I could close it and open a different one. So this little function, all it does is calculate a margin of safety based on the in-plane stresses and the von Mises stress. It's very simple. Here's a phony allowable. Everything's in SI units, megapascals. And you'll see here when I'm specifying the stresses, all I have to do is give it nx over t. I didn't have to define nx, I didn't have to define t. The program already knows what those are for every element. So let me just show you the quick guide here. I can grab it. So for these element types I showed you earlier, all of this information is available to you inside this user-defined function. So you'll see that T is available to me, that's the thickness of the element, NX, NY, NXY, my moments, my shears. I could write an equation based on the material angle if I had to, or I could do something with the element offsets. And all the variables defined for each element type are written in this quick guide. So if you're dealing with C-beams and bars, these are defined for you. And for C-bushes, these are defined for you. Moreover, when you're writing a user-defined function, you already have the Python math module available to you. So you'll notice that when I define my von Mises equation, I called the math module without having to import it and use the square root function. So I think that's pretty useful. I hope that people will use that a lot. It's very nice that you have model information, thickness, and results already available to you. And when this function is run, it's run for every single element. that you specify. So I think that's very nice. And you can calculate your margins of safeties and everything. So let's go ahead and run this function and see what happens. We'll leave all the other inputs the same and see what the output looks like. Alright, didn't take that long. The old output was actually overwritten. So we have a new output, same file name. But inside this output, we actually have our new variables from the user-defined function. Here you see the FTU is the same for every element in every load case. Further towards the right, you'll see the von Mises stress being calculated. And here's the stress components we calculated. And whenever a variable named MS is defined, it's always reported at the end. And here they are, margins of safety. They look quite high, but that's probably because of our phony, the magnitude of our phony allowable. So anyways, one thing to notice here with these variables is we are only looking at values. There's no equations created here. But if you wanted to create your own equations in Excel, it's quite easy. You remember what it was. The FX stress component was simply NX divided by T. See, it's going to report the exact same thing. And that's that. I hope everyone sees that as being something useful and might save you a lot of time in your analysis. Just close it without saving. So the last thing we'll cover is the factor and combination files. We'll leave everything else the same and just turn these on one at a time. So we'll start with the factor file. Check this checkbox, everything lights up, turns on. If you noticed over here, I did already create a factor file. I will show you its contents. I'm dealing here with two load cases, and it's very simple. All I have to do in the factor file is specify the load case, comma, and the factor. The factor can be anything you want as long as it's a number. And I do recommend to leave in the decimal to make sure it reads as a floating point format. So this is very simple. Specify that file. And before I do anything, I want to rename this output file so that we maintain the unfactored output so that we can check the results. So we'll analyze it again. Alright. Now we have a new output file and the old output 0. Let's open up the new one. Can't really tell anything's happened. But if we also open up this one and copy and paste some of the old results into the new, we can run a quick check just to make sure that we're actually seeing the proper factor. So assuming everything is in the same order, you see that we do in fact have a perfect factor of 1.5 on load case 5400. And based on those results, I'll assume 5300 was also factored perfectly. And that's that. The next demonstration will be combinations. So if we're giving it the file and you open up this combo file I have prepared, there's only one combination right now since we only have two results, two load cases. Basically, the format of this file should be new load case ID followed by two existing load case IDs. And then this new load case ID will be the combination, addition of this, the results from this load case, added to the results from this load case. So let's specify that file and rerun it. Verify the output. We'll leave the factor on. We'll do both at the same time. Alright. So that overwrote our factored only results. Now we open up the new results, we'll see, oh, we got a lot more output here. Here's our new load case. It's actually indicated by the none ID in this column. But you see that you still have your element ID here. And so just to confirm that this was properly combined, I'll just add these two cases together. If I can get it all to fit in the same window, there they are. There's the equation. Adding those two components together should equal this, and in fact it does. So we can safely we have confirmed that we're actually combining cases correctly. Everything's working, and you'll see, if you remember, these are our factored results, so it's the factored results that are being added together. So factoring happens before combining, which is what we want. And so that's that. That's everything the tool does. If you have any questions, please feel free to use the make a request form on the website, or simply leave a comment at the bottom of this tutorial. Thank you for watching this tutorial, and I hope everyone finds this tool very useful. And let me know if you have any other ideas or requests, and I'll be happy to implement them. Thanks, guys.